Hello all. In this video, we are going to take a closer look at hill climbing, the algorithm or algorithms as it turns out, and we'll look at how they work, and we'll take an example, a simple example from the traveling sales problem to illustrate the general process and then the specifics of the actual algorithms. We'll take a look at some pseudocode as we go along the way. All right, so we'll look at the full algorithms in a minute. This is a very high level hand wavy view of what hill climbing is doing. So we start out picking some state as our initial state. How this gets to be varies from implementation to implementation. It could be that you have that coming in from outside. You're told what the initial state might be, but also often with these algorithms, we just randomly generate a starting point. We just need some state in the space for us to start our search from. We take that initial state, we compute its value by the objective function, and then we go into a loop that goes indefinitely until we find the optimal solution, or we run out of time and we just have to stop the search, or the search tops out at one of those local maxima and we just can't go any further. So what we're going to do is to take the current state and generate all of its neighbors. There are variants where we don't generate all the neighbors, but we generate its neighbors, some subset or all of them, and we compute their values with the objective function. So we have to evaluate their quality. And what we'd like to do is to pick the neighbor that has the largest value and make it the current state, so long as its value is greater than the current state's value. If you hit a point where all of the neighbors are of lower quality, you're at one of those local maxima and you just stop the search at that point. So I'm leaving out a lot of details here, but this is the fundamental idea. We're going to take step by step by step, moving from where we start, hopefully up as much as we possibly can until we get to the maximum that we can find. All right, I want to illustrate this before we look at pseudocode and get into more gory details and variations, I want to start by looking at a simple example. So we are going to look at the traveling sales problem. If you've taken an algorithms class, you probably know this problem already, but I'll just describe it. We are imagining that the way the problem is phrased is we have these nodes in a graph. They represent cities. And we have a traveling salesperson who needs to go and visit all those cities and return back home again as efficiently as possible. So we want to be able to pass from one city to another and return to the start without ever repeating a city. We don't want to go to a city more than once. So we don't want to go from A to B, B to C, C back to B, and then from there to D and A. So we visit each city once and return at the end back to our starting point. So our goal is, this is a weighted graph. It's different. It's less expensive to go from A to B than it is to, say, from A to D. So each path has a certain cost associated with it. This is an optimization problem. We want to minimize the cost. This is actually better thought of as gradient descent, but we'll make it work thinking of it as hill climbing. So what is our state space? This graph is not our state space. That's not how this works. Each state in the state space, when you have local search, needs to represent a solution. So what we need is some ordering of the vertices, because if you think of the problem, if I go from A to B, I can never revisit B again. So then it's going to be either C, D, A or A, B, D, C, A, right? We only have those two choices. If we just consider all the possible orderings of this, of the vertices that are in the graph, each ordering is a unique set of paths, and that is a potential solution to the problem. So A, D, B, C, A, D, C, B, A, B, C, D, A, B, D, C, and so on. You could narrow this down by saying, and we're going to anchor it so that it always starts with A. And then you don't have really very many other paths that you have to consider for this small example graph. So a singular state in our state space then is going to be some ordering of the vertices. So like A, B, C, D, and it's kind of implicitly here that we then return back to A at the beginning. All right, one of our issues here is that we want to evaluate each state. So we want to generate a sequence and then evaluate it in some way. We have two choices here because this is in fact a minimizing problem. We want to take the minimal cost path. We could just think of this as gradient descent and in each step pick the state with the lowest cost each time. Or we could imagine doing something crazy like just negating the costs for the purposes of the search. And then we maximize it. So then the maximum cost possible would be 0. That's the maximum value if we negate all of the costs, and they turn from being gradient descent into being hill climbing. I think I'm looking ahead to see. I'm just going to treat this as gradient descent. When we work on examples in person, we will make them be hill climbing, but it's just easier for me to think through this as gradient descent. All right, so we have A, B, C, D. That's one of our potential solutions. We need to define what it means to be a neighbor of A, B, C, D. And there are lots of different ways you could do this. We want to have a significant number of neighbors, but not a bajillion neighbors. So we don't want every other permutation to be a neighbor. That would change the problem significantly. What we want is something that's similar to this one, but yet not exactly identical, because then it would be this one. So what I've chosen in this case is a neighbor is going to have 2 adjacent vertices, and only 2 from the original swapped. So A, B, C, D is our original. One neighbor would swap the A and B, and so we'd get B, A, C, D. One neighbor would swap the B and C, A, C, B, D, and one neighbor would swap the C and D. So not everything in the space is a neighbor, but we have some number of neighbors, and they make sense. There is some similarity among them. The general idea being that if they're similar solutions, they probably have somewhat similar values. And so searching in a place that has high values is a promising way to find even higher values. All right, so then we're gonna walk through this example and take a look at what would happen. Our current state ABCD has the cost as shown here, 3 plus 12 plus 25 plus 9, which is 49. And I'll go back to the graph momentarily. So that was ABCD, right? ABCD. So we have 3 plus 12 plus 25 plus 9. That's the cost of that path. I'm not going to keep going back to that graph every time. So we add up those costs, we get a total cost of 49, and then we generate their neighbors and calculate all of their costs. So for each of these, I've gone back to the graph and figured them out. We have 2 that have a cost of 48, and we have 1 that has a cost of 41. Depending on the algorithm, we might for sure pick our lowest cost one. In this case, remember here we're doing gradient descent, so we're going to pick things that go most steeply downward. But you could have also variations where there's some randomness involved. But we're going to pick ACBD, and it has a cost of 41, and we will look at its neighbors. So ABCD is one of its neighbors, and the others are CABD, where we swap the first 2, and ACDB, where we swap the last 2. All of these have higher costs than our lowest cost neighbor, so we have hit a local minima in this case because we're doing gradient descent, and there's nothing more that we can do. So this is the best solution that we found. Is this the optimal solution, or is it not the optimal solution? That's something that you might need to think about on your own and kind of work through for yourself. All right, so what are the benefits of hill climbing? Well, if you don't have huge numbers of neighbors, then you find nearby maxima or minima fairly quickly. because you're always moving the most steeply uphill for a hill climbing problem or the most steeply downhill for gradient descent. So it's fairly effective when you have a limited number of neighbors. It does have issues, and so we'll have some variations on hill climbing to address these issues, and some of the fancier algorithms are also intended to help us address some of these issues. So one big issue is there's no guarantee we're going to find the global maxima or minima. We might very likely find a local optimum, a local maxima or a local minima, and not the one that we'd like to find. So if there's a way for us to recognize that we're not at an optimal solution, there are methods that we can add on to this algorithm or alternate algorithms we can use that will try to help us to solve this problem. This algorithm struggles a little bit with plateaus or flat regions. Because so one possibility is that you code up the algorithm in such a way that if all of the neighbors are equal to the one you're at, you just stop. That isn't so bad if it's a peak that has a flat top. But remember, there was the image where we had the flat part and then it was a shoulder of a mountain, so it went further up from one side. If that's the situation, then not being able to navigate the plateau is a problem. But the other problem is if you do allow it to move sideways so that if it has a neighbor of equal quality, it can actually take that neighbor, you get into the plateaus and the algorithms tend to just randomly wander. They don't have any direction. You don't have any way to say, oh, you're going in circles and you're revisiting the same states over and over. We don't always keep track of all the states we've generated so far with these algorithms, and so we don't necessarily know that it's not making progress. So we need some mechanism to help us address that. Maybe it's keeping track of what neighbors we've generated. Maybe it's just incorporating randomness so that it continues to walk in a random way and eventually will cross the space. The other big issue with hill climbing itself is if you have a lot of neighbors, then it bogs down. So in the example that I did before, if we go back to our pseudocode, in the example that I did before, we only had 3 or 4 neighbors for each state. But imagine a space where I have 1,000 neighbors. If there are 1,000 neighbors, and it's not very expensive to calculate the evaluation function, it might be a little slow. But there are also situations where you have 1,000 neighbors and it's expensive to calculate the objective function, the evaluation function. Relatively expensive. This can really bog down a great deal. And we'll look at some examples of that when we're in person. All right, so down here we have some variations. I want to actually go and look at the local search algorithms that I have in pseudocode, and we'll talk through them. And I want to give a shout out here to the Geeks for Geeks page about hill climbing. Some of the names for some of these variants I pulled from their information because I've just thought of them as different variants in the past. All right, so we're going to start with this variant, which I think is what most people think of when they're talking about hill climbing. This is what they think of. It's the one that I described in my high-level general pseudocode as well. So we are at a particular start state, and we go into the loop just as we mentioned before. We generate the child states. If there are, for some reason, no child states, then that's like a strange situation, but it would mean that you're in a dead end and there's nowhere to go, so you just end the search with the current state. Otherwise, we are going to figure out which neighbor has the highest value. In doing that, we have to actually generate the value for all of the neighbors. If that neighbor's value is less than the current value, remember this is hill climbing, so we're optimizing upward, that means that all the neighbors have lower value because this neighbor right here, this is the best neighbor we had. And if the best neighbor is not as good as our current, then we want to stop the search and return the current because we've found a maxima. On the other hand, if the neighbor is better than the current, we go to the else and it becomes our current and we go on from there. So at each point, we only are really paying attention to one state. We calculate that state, we look at its neighbors, we pick the best neighbor we can, and then we move to that next neighbor and we start the process over again. I'll try to put some links for you for if I can find some good animations of hill climbing, because it's also helpful to actually go through it to understand what the algorithm is doing. So now we're going to look at the simple hill climb. At least that's what Geeks for Geeks called this version. This one takes a slightly different approach. It doesn't look at necessarily at all neighbors. So if you have a lot of neighbors or your evaluation function is particularly expensive, this might be a good variant. It doesn't have any randomness in it, but it does simplify each step of the search, and it isn't as concerned with finding the absolute best neighbor. So the start is the same. We set up a current state that we're keeping track of. We're going to loop until we decide we're done. We're going to gather all of the neighbors of the current state. We still have our strange case when we don't have any neighbors. Otherwise, we have a little loop here, and that's what makes this kind of critically important. We're going to store the current state into a separate variable just so we can keep our hands on it. And then we're going to start looping through the children. And if the child is of lower quality than its parent, than the current state, we'll just do nothing but keep looping. But if the child's value is an improvement on the current state, then we're going to set current to be that child. Notice this is just the first state we come to that has a higher quality than the current state. It's not necessarily the one that has the biggest higher quality. It's just the one it's just the first one we run across that's better than our current. And then we break out of the for loop. So we stop looking at the children here, and we're going to go back around the whole while loop. The if statement here at the bottom helps us capture the example where we've hit a maxima. So when we're done with the search because we've hit a maxima. So if we were to go through this for loop, and we never found a child that was better than our current one, then current would still be the same at the end of the for loop as it had been before the for loop. And then previous would be equal to it, and we would stop the search and just return current at that point. So this is the case where we found the end of the search. That only happens if the for loop runs all the way to its end without finding a neighbor that has a higher quality. All right, I'm going to flip back to my notes just for a moment, because the other approach that I want to talk about right here is stochastic hill climbing. Stochastic in this case meaning involves randomness. And there are different variations of stochastic hill climbing that I have seen in different places. There is a variation that says generate all the neighbors, evaluate all the neighbors, but don't necessarily always choose the most optimal one. So what you might do is to have some kind of random method like resampling that you use in order to choose among the neighbors. So there's some chance that you might not choose the most optimal one. Adding in a little randomness to these searches actually can be beneficial because it can cause us to explore more of the space, and maybe we'll find our way to the foot of the hill that is the best instead of going up a local one that's nearby. There is another variation that's kind of similar to the simple hill climbing that I was talking about before, where you don't generate all of the neighbors. Maybe you generate a fixed number and you pick the best among them. Maybe you generate them one at a time, and there's some random probability that you'll pick each one that's a function of its quality. So higher quality ones will be more likely. I think I actually have some notes over here. So let's go and just kind of take a look at them there. So yes, stochastic variants add randomness to the mix, and I basically have talked through most of these already. Instead of generating the children in a fixed order, you generate them at random, and otherwise you follow the simple variant. So you generate one, and then if it's better, you take it. You could generate a random set of children, or all of them, and choose among them using resampling, which algorithmically we refer to as weighted roulette wheel selection oftentimes. Or you could generate children at random, choose a child to be the next state based on its value, and have that be a function of its value. So maybe there's a chance that things that are lower quality than the state that you're at might get chosen. But if you run across a neighbor that has a really high value, it's going to have a much greater chance of being chosen. All right, so these are variations on hill climbing that help us out to resolve some of those issues that I had mentioned before. So the stochastic variants, can allow us to explore plateaus because they allow us to use some randomness to travel through them. They can allow us to avoid local maxima, or at least have a chance of not always going up the same local hill. And they can handle too many neighbors fairly well. There's still no guarantee we're going to get the best solution. That's just the nature of these algorithms. They could be misled. They could go up a hill that leads to a local maxima instead of to the global maxima we would like. There's one other kind of hill climbing I want to mention, and that's random restart hill climbing. I feel like this is like the total smash approach. So what happens with this one is, instead of, when you reach your local maxima, instead of just stopping, you try to evaluate how good it is. And if it's not optimal, then you just start the search all over again. You basically generate a random state, you set that to be your current state, and you continue running. So this is kind of, I don't know, this seems like a very hacky approach to me, but it is actually a commonly used approach. So if at first you don't succeed, start from somewhere else and see if you can succeed better. That's basically the idea of random restart hill climbing. All right, so we've talked through a number of different variations on hill climbing. In future videos, we will take a look at beam search and also at genetic algorithms, which mainly doesn't sound like it should be a local search, but it's remarkably similar. And we may also talk about some other algorithms as well. I will see you very soon.